In this lecture, we will talk about developing your analysis plan. You have gone through a series of steps now. You developed your construct and your survey instrument. You sampled the population and distributed the survey to the participants in the sample. You collect the responses, and finally, you have your data. So in this lecture, we will talk about getting your data ready for analysis and what kind of test statistics are appropriate to best capture the results from your study design. Before jumping right into the analysis, it is really important to understand your data well. I saw from my experience that if you do not plan your study well, then when it comes to analysis, you will always have some problem. Either you have missed to collect information on some important variables and now you are not comfortable in being able to generalize your study results to the population, or sometimes even if you have collected the information, you have missed out on important details. Additionally, you will realize the importance of having a clear and good hypothesis when you are analyzing your data. That means clearly defining what is your explanatory variable and what is your response variable. Also thinking ahead of time and putting in due diligence to understand what could be potential confounders, moderators, and mediators would be important so that when you develop your survey instrument, you are making sure to collect relevant information on these variables. Additionally, from your study design, you will know whether you have single time point data or multiple time point data. If you are doing a cross-sectional study, then you have single time point data. If you are following the participants over a period of time and recording data at many time points, you have multiple time point data or longitudinal data. For example, if you are recording the CD4 count of HIV-positive patients over time, you have longitudinal data. This will influence your analysis and choice of statistical test. It is also important to understand the nature of independent variable and your outcome variable, and also the nature of other variables in your study. In the coming slides, we will learn more about the nature of these variables. This diagram shows that our survey research is a cyclic process, with one step leading on to another. There is a relationship. Decisions you take upstream affect the results downstream. It is important to be able to see the overall picture. You should have your hypotheses ready right when you conceive the idea of the study. At the same time, we define the study population from which the sample is taken. Then we distribute the survey instrument we have developed to the participants in the sample. That gives us the data. We then analyze the data and finally generalize the results back to the population. When you first get your data, eyeballing it would be useful. Look at what variables you have. Try to understand them. The level of measurement of the variables in your study is going to inform the analysis. It is important to have a knowledge of the variables during the design phase of the study itself, actually. Understanding the nature of the variables is very important. Especially the nature of outcome variable is important. If you have categorical variables, then for a descriptive analysis, you are going to get the proportion, not mean. If you have continuous variable, such as a body weight, then probably mean or a median will make sense. Likewise, if your outcome variable is categorical and dichotomous, then logistic regression is a good option. However, if you have categorical outcome variable but you have more than two levels, then you can choose for ordinal logistic regression or multinomial logistic regression based on whether the level of measurement of the outcome variable are ordered or not. Similarly, if your outcome variable is continuous, then linear regression will make more sense. If you still want to do a logistic regression, then you should first recode and convert that continuous variable into categories. So I would say when you first get your data, don't right away jump into multivariate analysis. Take your time, get a feel of the data, eyeball it, do your descriptive analysis. This will help you see if there is anything odd or unusual going on with any of the variables. Okay, processing the data. I don't really see a this way or a that way of processing and cleaning your data. As long as you know what you are doing and what you are doing makes sense, that is okay. I would still say it is very helpful to process your data in an organized way. If you are going to do a logistic regression, then the values of your outcome is usually coded 1, 0. Also make sure you are coding the values of your variable properly. Say you have an ordinal variable, socioeconomic status, with values as low, middle, and high. then make sure that you code them accordingly, such as 1, 2, and 3 for low, middle, and high SES. When you conduct the statistical test in your software, the lowest value, that is low SES here, is usually treated as a reference, and the estimates will be generated for the other levels of the variable in comparison to the reference value. As I said before, you can collapse the categories or convert continuous to categorical variables. Keep in mind that when you collapse categories, you are losing some granularity of information that may introduce residual confounding. For example, you have a variable called years of cigarette smoking, captured as a range from 0 for no smoking to 1, 2, 3, and so on years of smoking. And now if you collapse this variable to a dichotomous variable with just two values, smoking, yes and no, well, you are really losing important information. You are losing all the information about the years of cigarette being smoked. And if smoking is an important variable for your study, then it could potentially bias the effect estimate. Likewise, you can combine variables also. We do this often in factor analysis or principal component analyses. When you make these decisions, really think of the influence it will have on the overall construct of the study. Okay, coming on to statistical test. Which statistical test you will use for your data is largely determined by the type of data you have, whether cross-sectional or longitudinal, nature of your response, and the explanatory variables, and the analysis you will do, whether descriptive or a test of association. The nature of the dependent or the outcome variable greatly influences your choice of the statistical test. We will look at this in the next two slides. And usually for longitudinal data, you have a completely different approach. And we are not going to go over this here. Alright, so mostly when you write up the results of your study for your publication, say, you are going to have most likely a table 1. So table 1 is usually the descriptive table, the univariate analysis. You are studying just one variable, its mean or proportion and variability. For example, mean age, percent of females, etc. In a bivariate analysis, you study the relationship between two variables. This can be thought of as a crude or unadjusted analysis. You are not controlling the effect estimate or your result for influence from a third variable, which could be a confounder, moderator, or a mediator. In a multivariate analysis, you study the effect on the outcome from an exposure variable after adjusting for third variables that you think are important. Most often, these third variables would be your confounding variables. These are examples of univariate analyses, bivariate analyses, and multivariate analyses from a study that I conducted among tuberculosis patients in India. This is an example of how the information is presented when you come at the stage of writing and publishing your results. It is really there to just show you how the information is presented and how a univariate, bivariate, or multivariate analysis look like. You really don't have to understand the results or the meaning of the variables, etc. The outcome variable for the bivariate and the multivariate analysis is whether the patient had resistance to a particular anti-TB medicine called rifampin. And most variables presented here are categorical. Age is continuous. Gender has 2 levels of measurement. Most other variables have more than 2 levels of measurement. The outcome, rifampin resistance, is categorical and dichotomous. So I did a logistic regression to test the relationship between the independent variables and the dependent variable. In this example, the risk group is my explanatory variable of interest. So from the results of the multivariate analysis, you can see that in that variable under risk group, you can see that compared to the new patients, which is my reference group, patients who have failed category 1 or category 2 antitubercular treatment, abbreviated as ATT here, are at statistically significant increased odds of developing resistance to rifampin after adjusting for potential confounders, age, gender, occupation, and smoking history. This table is a revision of some of the common test statistics we use for measuring the outcome. In a univariate analysis, it could be simply mean, median, mode, or proportion. We can do a bivariate analysis using various statistical tests. Chi-square test of association is commonly employed. It tests for presence of a significant difference between the observed value and the expected value of the outcome in the categories of the explanatory variable. And for two linear variables, we can do Pearson's correlation test. It measures the correlation coefficient R. 1 means perfect positive correlation, 0 for no correlation, and -1 for perfect negative correlation. T-test and ANOVA will measure the difference in means. T-test is used for comparing means of two groups, and ANOVA is used for comparing means of more than two groups. ANOVA is basically analysis of variance. A relative risk or incidence rate ratio can be calculated by generalized linear models or Poisson models when you have count data. And you can hand calculate it also. It is simply the incidence of disease in the exposed group divided by the incidence of disease in the unexposed group. Most times you can simply calculate odds ratios, and it is a good estimate of relative risk when the prevalence of the health condition is less than 10% in the population. If the prevalence is greater than 10%, then the odds ratio and the relative risk estimates may quite differ, and you may choose to specifically calculate the relative risk. For the purpose of this class, I'm okay if you generate series of 2 by 2 tables to show the relationship between the dependent and the independent variables in your assignment and your research plan project, and calculate odds ratios in bivariate analyses. You can get a little bit more advanced and calculate relative risk or odds ratios using logistic regression in the multivariate analyses. The odds ratios or relative risk in multivariate analysis differs from bivariate analysis in that in multivariate analysis you are controlling for third variables. However, you are not required to perform multivariate analysis for this class, and it is really not going to make a difference to your grades. And in linear regression, you are modeling the mean of outcome given the exposure. And in multiple linear regression, we are calculating the mean after adjusting for third variables. And hazard ratio is another test statistics that is quite commonly used, and it is obtained by Cox proportional hazard regression. So these are all really revision of your biostats background. Okay, so this is an example here. You can basically choose what test statistic you would like to use in this example. Your independent variable is categorical. You have categories of income level, low and high. And your dependent variable is quantitative, say body weight. And your null hypothesis is mu1 is equal to mu2, or mu1 minus mu2 is 0, which are the same. And your alternative hypothesis is mu1 is not equal to mu2. Basically, mu is mean. So which test statistic you will use? So this is two sample t-test for difference in means. Okay, let us look at another example. So here, again, your independent variable is categorical, categories of income level, low, middle, and high, and you have dependent variable as body weight. Your null is mu1 is equal to mu2 is equal to mu3, and alternative hypothesis is not all means are equal. So that is mu1 is not equal to mu2 and mu2 is not equal to mu3, or mu1 is equal to mu2 but mu2 is not equal to mu3, or mu1 is equal to mu2 but mu2 is not equal to mu3. So these are all different options for your alternative hypotheses, and the samples are drawn independently. So in this scenario, which test statistic you will use? Okay, so here we are going to use ANOVA. So ANOVA uses F statistics, which basically is variation among sample means divided by the variation within the groups. So basically T statistic we use when we have two groups, and when we have more than two groups, then we use ANOVA. Okay, that brings us to the end of the lecture on developing our analysis plan and statistical test.